So welcome you to this module. Last few modules we were discussing about affine invariant estimation. So the model is as follows. So suppose you have a sample or a data x1, x2, xn, which is jointly distributed, and it is coming from a distribution function f, which belongs to the parametric family of distribution functions f theta, which is characterized by two parameters, mu and sigma. Mu belongs to whole of R, sigma belongs to 0 to infinity. So let me call this as theta, where f theta of x1, x2, xn is same as f of x1 minus mu sigma xn minus mu by sigma for every x belonging to Rn and mu sigma belonging to theta. What we assume is that functional form of this is known. So that means what is unknown in this whole model is the unknown parameters mu and sigma. And so one can talk about estimation of different functions of mu and sigma. So the first thing which we tried to look into is appropriate group of transformations under which this problem remains invariant. So what we saw is if we had sigma is equal to 1, then it was a location kind of a family, and then appropriate transformation there was GCX, which was x1 plus c, x2 plus c, and xn plus c. If all mu were 0 and it was only x1 upon sigma, xn by sigma, then appropriate group of transformation was GBX, BX1, BX2, BXn. Now in this case, what we saw is appropriate group of transformations could be G of BC, where B is positive, C is in whole R, where GBC of x1, x2, xn is same as bx1 plus c, bxn plus c. X belongs to Rn, B positive, C belongs to R. So we saw that this family of distributions remains invariant under this group of transformation. What does that mean is, if I apply GBC to random vector x, that means if I consider bx1 plus c, bxn plus c, I again get a distribution in the same family, except that now your mu changes to b mu plus c, sigma changes to b sigma. So what we know in this is GP is invariant under G with induced group of transformations on parameter space as G bar, which is collection of all those G bar BCs, such that B is positive, C is in R. And what is G bar BC mu sigma? We have seen that if you apply bx1 plus c, bxn plus c, I get a distribution function as mu gets replaced by b mu plus c and sigma gets replaced by b sigma. So this becomes b mu plus c and b sigma, where b is positive, c belonging to R. Now in this case I can talk about estimation of sigma or sigma to power r. I can also talk about estimation of mu. Now estimation of sigma to power r we already did in the last module. So let us start with estimation of sigma, which is the case 2. Estimation of mu. So the first thing I have to identify is what should be the appropriate group of transformations on the xn space of mu. Now note that mu can take any value in R. So my xn space is R. So I need to identify what should be the group of transformations on Xn space. For that, what I need to see is where this mu gets transformed to. So under the transformation G bar BC, mu gets transformed to B mu plus C. So my Xn, because finally I'm estimating mu, so my Xn also should change accordingly. So this suggests that I should consider group of transformations G tilde as G tilde BC, B greater than 0, C belonging to R. And what should be your G tilde BC? G tilde BCA should be same as BA plus C, B belonging to R. Sorry, B positive, C belonging to R. And your A is anything in the Xn space which is whole real line. So now I have to identify what are the kind of loss functions which would be invariant under. So this is acts on Xn space A. So I need to identify what should be the structure of my loss function so that the estimation problem at hand remains invariant under this group of transformation G. So L theta A is invariant under G if and only if. What happens? L theta A, which is L of, so I apply G bar BC theta. So I look at the loss in the transform problem, which is L of, in transform problem theta is G bar BC theta, A is G tilde BCA. The loss, total loss in the transform problem should be same as the loss in the original problem. L theta A for every theta belonging to capital theta, A in Xn space, B positive, C in R. So my loss function should possess this property. Let us try to see what it is. This is equivalent to saying that L of, what is G bar BC theta? Theta has two components, mu and sigma. Under G bar BC, mu goes to B mu plus C, sigma goes to B sigma. G tilde BCA is nothing but BA plus C. Should be same as L of mu sigma and A. And this would happen for every theta belonging to theta, A belonging to A, B greater than 0, and C belonging to R. So the first thing what I do is I have a lot of degrees of freedom in terms of parameters B and C. So the first thing I choose is I take B to be 1 upon sigma. Note that my B is positive. B can take any positive value, so I can choose B to be 1 by sigma. And then C I choose to be minus mu by sigma. So this implies that L of 0 by taking B to be 1 by sigma and C to be minus mu by sigma. So L0, 1, B as 1 upon sigma minus mu by sigma, so that is A minus mu by sigma is same as L of mu sigma A for every theta belonging to theta, A belonging to script A, B positive, and C belonging to R. So what does that mean? That means my L mu sigma A should depend on mu and sigma only through A minus mu by sigma. So it should be a function of A minus mu by sigma. So this implies that L theta A is same as some function of theta belongs to capital theta, A belongs to script A, for some function W from R to R. So if my loss function is invariant, it has to be of this type. Now let's look at whether any loss function which is of this type is invariant or not. So what I have to do? I have to see whether L B mu plus C BA plus C, when I consider B mu plus C, BA plus C, CC gets cancelled, B becomes common, but theta goes to B sigma, so BB gets also cancelled. So that is, any function of this type is invariant. So what I conclude is L theta A is invariant under G if and only if my L theta A is of type W A minus mu by sigma, theta belong to capital theta, and A belong to. So my loss function is of this type. Then only you have an invariance. So what I assume is my loss function is of type 1, so that the estimation problem at hand is invariant under G. So suppose that loss function is of type 1. So that means it is a function of A minus mu by sigma. So that the estimation problem is invariant under G. So I assume W to be convex function so that I can restrict only to the non-randomized decision rules. So assume that because if W is a convex function, then L theta A, which is WA minus mu by sigma, would be a convex function of A. So assume that Wt is a convex function of T, which basically implies that it is enough to consider only non-randomized estimators. Only non-randomized estimators. So what I do is I consider only those non-randomized estimators which are invariant. That is what the principle of invariance demands, that you restrict only to the class of invariant estimators and then try to find a best estimator over there. So Di, suppose, is a class of all invariant non-randomized estimators. So let us try to see what should be the form of. Now I try to see what should be the structure of an estimator in Di. Now note that delta belongs to Di if and only if G tilde, sorry, delta of G tilde, G of BC x is same as G tilde. So that means I transform the data and apply my estimator. That should be same as the estimator in the transform problem. G tilde BCX. What does that mean? This is equivalent to saying that delta of Bx1 plus C, Bxn plus C is same as G tilde B Cx is nothing but delta of x1, x2, xn plus C. So first I take B to be 1. So for every B positive and C belonging to R. So first I take B to be 1. This implies that delta of x1 plus C, xn plus C is same as delta of x1, x2, xn plus C for every C belonging to R. All right, good. Now what I try to play with C. So I can take C to be minus xn. Then if I take C to be minus xn, then that means delta of x1, x2, xn minus xn. That goes over there. So that is same as delta of x1, x2, xn is same as xn plus delta of x1 minus xn, x2 minus xn, xn minus 1 minus xn. Xn minus 1 minus xn and 0. Basically, this is nothing but d1 and this is dn minus 1. So this is same as xn plus psi times d1, d2, dn minus 1. So if my delta is invariant, then delta would be of the type xn plus psi d1, d2, and dn minus 1. So that means xn plus some function of d1, d2, dn minus 1. Now I try to use the degrees of freedom which I can get by choosing C to be 0. So also I take C to be 0, so that means d of bx1 bxn should be same as b of, sorry, this should be b here, right? Should be same as b of delta of x1, x2, xn. I apply this property in star. So what does that mean? That means this quantity where under b of x1, b of x2, b of xn becomes b of xn plus psi of d1 was x1 minus xn. So it will be b of x1 minus xn, so which will be b of d1. So b of d1, b of dn minus 1 is same as b times delta of x1, x2, xn. So that means b times this quantity, so which is same as b times xn plus b times psi of d1, d2, dn minus 1. So bxn gets cancelled both the side. So that means psi of b1, b2, bdn minus 1 is same as b times psi of d1, d2, dn minus 1. But now recall, what was the structure of a scale invariant estimation when you are estimating sigma? When you are estimating sigma to power r, it was psi of b d1, b dn minus 1 is same as b to power r psi d1, d2, dn minus 1. So it is exactly the structure of any invariant estimator of sigma. So that means this psi is some invariant estimator of sigma. So this implies that psi is an invariant estimator of sigma. So what does that mean? That means my delta of x1, x2, xn is same as xn plus psi of d1, d2, dn minus 1, and this is an invariant estimator of sigma. But just if you recall your module on estimation of sigma, any estimator of sigma can be written as, in terms of any given estimator, divided by u star w. So let delta 1 be a given estimator of sigma, then psi d1, d2, dn minus 1 can always be written as some function of w from your estimation of sigma multiplied by delta 1d. Where what is w? Where w is d1 minus dn minus 1 by dn minus 1 minus dn minus 2. Then dn minus 2 minus dn minus 1, sorry, d1 d2, then dn minus 2 minus, sorry, d1 minus dn minus 1, dn minus 2, sorry, d1 minus dn minus 2 minus dn minus 1 by mod of dn minus 2 minus dn minus 1. Right? That is the form of this. So what do you conclude from here? So what you conclude is if delta 1 is a given affine estimator of sigma, then any affine estimator of mu would be of the type so you can write down delta x equal to, implies that delta x equal to xn. So let me just note, let me note that xn minus, I can write down that as u of w. You see, psi you can replace by psi, so you can replace this sign by minus. That doesn't matter, right? Minus u of w into delta 1d. Now note that this xn itself is a location invariant estimator. Why? Because if you apply bx1 plus c, bx2 plus c, and bxn plus c, xn changes to bxn plus c, which is of the type b of delta x1, x2, xn plus c. So this itself is belonging to D. So the question arises whether I can replace it by any arbitrary estimator of mu, which is invariant. So one can easily prove that theorem. So let delta naught belongs to di. That means it is a location invariant, it is a affine invariant estimator of mu, and let delta 1 be an affine invariant estimator of sigma. So you choose one affine estimator of delta naught, one affine estimator of sigma, then delta belongs to di. That means delta is any other affine invariant estimator of mu, can be written as, if and only if delta x is of the type delta naught x minus u of w times delta 1 x. The proof is exactly on the same lines as we did before. First of all, any estimator of this type would be invariant. Why? You can look at, so what you have to see is delta of bx1 plus c, bxn plus c is same as b times delta x plus c. So delta of bx1 plus c, bxn plus c would be delta naught of bx1 plus c, bxn plus c minus, when you apply bx1 plus c to w. So x1 when I am applying to x1 plus c, I am applying to d1, it becomes, d1 is itself not depending on c, because d1 is x1 minus xn. So bx1 plus c minus bxn plus c, so that gets cancelled. So only b times something would come, b times something come over here, b, it just cancels. So w doesn't change. So this remains as it is. And this becomes, because it is a scale invariant estimator, so delta 1 of bx1 plus c, bxn plus c would become b times delta x1, x2, xn plus c. So it becomes, b becomes common over here. So it becomes b times, so that it easily follows, right? So one can prove this exactly on the same lines, the way we proved the structure of location and scale invariant estimator. So let me leave this as an exercise which is almost trivial. I have already given you a hint. So if any estimator of this type, you can easily see that delta of bx1 plus c, bxn plus c is same as b of delta x1, x2, xn plus c, because if any estimator is this type, then you know that delta is location invariant estimator of mu. So it satisfies delta naught of bx1 plus c, bxn plus c is same as b of delta x plus c. So it will be b of delta x plus c. Minus u, w does not depend. If you apply bx1 plus c, bxn plus c, w doesn't change because of this structure. C gets cancelled because of di's. And b gets cancelled because d1 minus dn minus 1, dn minus 1, dn minus 2, they will cancel the b. So this doesn't change. This would be b times delta 1. So it was b delta naught plus c, b delta 1. So b becomes common, then you get delta naught only. And c remains as it is. So any estimator of this type is invariant. And you have shown that any invariant estimator would be of this type. Why? That you can prove because delta naught is given to be invariant. So delta would be of this type, delta naught. Delta 1 would also be of this type. And then you can just prove it. So if to show that any invariant estimator of this would be of this type, what you do is you have to only find uw. So delta naught and delta 1 are given. So what I do is I take uw to be delta minus delta naught minus delta upon delta 1. And then you can show that delta naught minus delta upon delta 1 only depends on w. So let's complete the proof. Now once I have done that, what is r delta theta? It is expected value of w of delta, which is delta naught x, minus uw delta 1x minus mu by sigma. Now note that G bar acts transitively. We have already seen it while estimating sigma. G bar acts transitively, that means my risk function is constant. So this implies that, which is same as r delta 0, 1, which is expected value when mu is 0, sigma is 1, delta w of delta naught x minus uw delta 1x, sigma is 1, mu is 0. So now note that when I say that any invariant estimator of this type, my delta naught and delta 1 are fixed. So the only way delta in di are varying only through this function uw. So that means in certain sense, because delta naught and delta 1 are fixed, so in certain sense I have to find a function u which minimizes this. So what I try to do is I try to minimize this for every fixed w. And that gives me the result, the way we did it in the location and scale case. So I can write down theorem for any fixed w, let u star, which is u star of w, minimizes. So what I do is I write down this expectation as expectation of a current conditional expectation. Conditional is respect to w. And then when w is inside, in the inside expectation I have a conditional expectation, w fixed, so it is a constant. So I can think of minimizing this for every fixed w. Now note that minimizing thing is not going to depend on parameter 0, mu and sigma, because I have taken expectation under mu is equal to 0 and sigma is equal to 1. So that is why this is not going to depend on mu and sigma. So I will get a minimizing u which is independent of mu and sigma, because finally I have to put this in the estimator. So I cannot have a minimizer which depends on mu and sigma. So minimizes psi u, which is E0, 1 of w of delta naught x minus u delta 1x u belonging to R. Of course, such a minimizer would depend on what w has been fixed, so that is why star w. Then MRI of mu is delta star x. Delta naught was any fixed estimator which was given to me. location, affine invariant estimator of sigma, minus u star w I will obtain through minimizing this. My delta 1 was anyway given to us. So I start with a given delta naught, which is affine invariant estimator of mu, given delta 1, which is affine invariant estimator of sigma. I try to find out u star w, which minimizes, this would be conditional expectation, because I'll be writing down this as an expectation of a conditional expectation. So inside expectation, I'll try to minimize for every fixed w. So this is what the MRE is. Now, if you want to do it in this case of, so let's consider squared error loss function. What is the squared error loss function? L theta A is A minus mu by sigma whole square, which means my W is T square. So I try to see what should be my psi u, and I try to minimize that. So psi u turns out to be E0, 1, delta naught minus u delta 1x whole square, given w is equal to w. So if you want, you can write down this as u square E0, 1 delta 1 square x, given w is equal to w. U is a constant, right? Minus 2 times E0, 1 delta 0x delta 1x, given w is equal to w, plus expected value of 0, 1 delta naught square x, given w is equal to w. So note that if I take double derivative, psi double prime u is always greater than 0, because psi double prime u would be, this would be 2u. This gets, when this vanishes, you'll be getting 2 times expected value of this. And this is expected value of a squared quantity, which would be greater than 0 unless delta 1 is 0 with probability 1. And so that means derivative is equal to 0 gives me a minimum. So my u star w turns out to be derivative is equal to 0, 2u minus 2. So that means u star w turns out to be E0, 1 delta 0x delta 1x, given w is equal to w, divided by E0, 1 So now you can write down a small corollary which says let delta naught be any invariant estimator of mu. So that means it is a affine invariant estimator of mu, and delta 1 be an affine invariant estimator of sigma. Then, under the square error laws, the a minimum risk invariant estimator is delta naught x minus u star w delta 1x, where u star w is given by this. So let me write down this as star, where u star is given by star. It's very easy to find. So the only problem, so what you have to do is you have to identify one location invariant estimator, one scale invariant estimator, affine invariant estimator of sigma, one affine equivalent estimator of mu, identify as per your convenience. Find u star w, which would be either the quantity which minimizes this conditional expectation, or in the square error of loss, it would be exactly this quantity. Then you are done. So the only problem reduces to finding this conditional expectation. Now note that this W is ancillary. We have seen it many times. As I said, that BB gets cancelled, CC gets cancelled. So note that W is ancillary. That means its distribution does not depend on mu and sigma, because the way we have defined W. W is d1 minus dn upon dn minus 1 minus dn. Distribution of d1 does not depend on mu. It only depends on b. So it would be b times something, but bb gets cancelled because in W we consider the ratios d1 minus dn upon dn minus 1 minus dn. So W is ancillary. So here I am conditioning on an ancillary statistic. So if my delta naught and delta 1 were functions of complete sufficient statistic, then U star does not depend on W. And in fact, one doesn't have to compute this conditional expectation. So choosing delta naught, delta 1 as a function of complete sufficient statistic helps in evaluating U star as then delta naught, delta 1 and W are independent. If they are independent, so conditional distribution does not depend on W, so that means minimizing thing will not depend on W. So this was about invariant estimation of mu under the affine group of transformations. So what we have done so far is we considered to begin with location invariant estimation, then we consider scale invariant estimation. Now in the last few modules we consider location and scale invariant estimation, which we also call as affine invariant estimation. So what I'll do in the next module is I'll consider at least few examples where I have a affine group of transformations, so that means location scale family, and I have to talk about estimation of mu. Estimation of sigma to power r examples we have already done. So that is for the next module, which we'll be doing in our next lecture. So thank you very much.